All right, I'll jump right in. My name's Allan and I'm an associate professor in the Department of Epidemiology and at the Institute at Brown for Environment and Society. And I wanted to talk today about improving our models of climate-related exposures and what that unveils when we better understand the temperature of the neighborhoods around us and the quality of the air that we're breathing. And part of my research uses data from satellites and from global models and from networks of sensors, bringing that all together to unpack what people are being exposed to and relate that to human health. So I have no financial disclosures, but the things that I want to talk about today are how we're improving on our exposure science. So figuring out what people are exposed to, what are the implications of having better models, better reconstructions, how does this advance climate and health epidemiology, where our goal is to leverage these large investments in satellite constellations to enhance exposure assessment using cohort studies and large registries and demographic information. So the premise of this research is that getting exposures right matters. That these exposures, whether we're talking about heat or air pollution or other climate-related exposures, they vary dynamically over space and time. So we think about the urban heat island effect, and I'll talk about some ways in that can be thought about, but it's not monolithic. There's actually a lot of structure. So another term that people have used is the urban heat archipelago, right? So a network of islands, because there are variations from block to block. They can be quite substantial. And the same is true of air pollution, right? We may only have a few regulatory grade air monitors in Rhode Island, but that doesn't mean that the concentrations of air pollutions don't change over pretty short spaces and in time. And so we need accurate estimates for our epidemiologic studies. If you lump everyone together, we'll talk about kind of the implications of that. And so one of the things that my group does is that we build geostatistical models, we use satellite data, and then we look at the implications of having better models. So what is that? How does that change our interpretation of these relationships? So I'll give some examples of where we're combining satellite-derived data with meteorologic data or topographical information and land use covariates. Two of the kinds of parameters that we're getting off of satellite data that relate to fine particulate air pollution is called aerosol optical depth. So this is a physics-based retrieval of retrieval is the term for an algorithm that's used to estimate a quantity. So it's a physics-based retrieval for light scattering. One of the effects of particulate pollution is, it used to be known more like smog, right, is that it causes a dissipation of light. And so that's what the satellite is able to estimate, how much has light, the light that we're anticipating should be reflected off the Earth's surface, been scattered. From that, NASA is estimating the aerosol optical depth, which is a quantity for the whole atmospheric column. And there's a problem with using something for the whole atmospheric column, which is that you or I do all of our breathing down really at the bottom of the column. And so if you have lofted aerosols, for example, coming from long-range transport of distal wildfires, that might cause a really beautiful sunset, doesn't necessarily pose a risk to human health until it down mixes, until you have those particles coming down to where we're doing all of our breathing. Nonetheless, it's helpful to have these kind of data because satellites are making observations even where we may not have local monitors. On the reconstruction of air temperature, we can use thermal remote sensing, so measurements in the infrared portion of the electromagnetic spectrum that are telling us about the surface temperature, the temperature of the skin of the Earth or that top layer where, wherever that may land. And then we use that to try to inform what the air temperature is. So we talk about temperature, we're talking about the temperature, usually it's measured at 2 meters of height is the standard. And so there's a relationship between the surface and the air. It's a complicated relationship, but in general, we'll talk about sort of dark, paved, impervious surfaces, right? Those both hold, they hold a lot of heat and then they heat up the air around them. So these are two of the metrics that we use. We also, increasingly, I'm interested in reconstructing humidity. Humidity is sort of an underappreciated component of thermal stress. And so one of the things that satellites do really well is we use them in meteorologic applications. There are specific wavelengths of light that's absorbed by water. And so the satellites, meteorologic satellites in particular, are very good at measuring the amount of precipitable water in that atmospheric column as well. So we layer this kind of information together. We use a technique that sort of extends what used to be known as land use regression. So this is some work that I did in Mexico City where there's only a few ground stations that are measuring air pollution, but you can sort of lay on top of that rich other kinds of spatial and spatiotemporal information about where the roadways are, different kinds of land use information, maybe meteorologic information. And then on top of that, you have these remotely sensed quantities that are being collected by satellites. So we bring all of this together to assemble these models, trying to reconstruct what the air pollution conditions have been in the sort of recent past. So some of the satellites that we use went up in around 2000 or 2002. And so a lot of our work is sort of thinking about the last 20 years. Some of the technical challenges, you get a staggering data volume from these satellites. Many of them have global coverage. So if you're only interested in a particular region, you need to be able to get just that area. There's lots of missingness in this data. So the satellite retrieval for aerosol optical depth relies on reflected sunlight. So you don't get any information at nighttime, you don't get any information when it's cloudy, and you don't get any information from the indoors, which is where a lot of us are spending most of our time. And then these are, complex retrievals. I explained how it's this indirect inference about how much light scattering there is. So there's a lot of complex atmospheric effects that lead to these being noisy measurements. And some of what my lab does is trying to clean up and improve on our inference for how much light scattering there has been, trying to improve the signal to noise relationships. So we make predictive models. I mentioned sort of geostatistical. So we're building machine learning models to reconstruct what's happened at ground stations. We are doing this sort of on the daily or sub-daily timescales. We're able to capture kind of complex relations and sometimes interrogate those models and see what are the features that were informing that model. What are the characteristics of a particular time and place that contribute to having higher estimated exposures, reconstructions of those exposures. But we've had to learn something about the structure of these data that's slightly different from sort of the machine learning that you hear about taking place in other kinds of applications, because the data come from they come from networks of ground stations, and so those networks have their own attributes related to where we've placed our training data, if you will, where the networks are has implications for how you build the model. So, and this is something that we worked on. So I'll give some examples, some maps from some of our models. We have daily high-resolution temperature and air pollution models for the contiguous 48 states. I also do quite a bit of work in Mexico, central Mexico. So this is average PM 2.5, so fine particulate matter. And this is showing it here sort of seasonally, but on the right, here's sort of zooming in, and this is what our reconstruction of PM 2.5 in the New York City region would have been for this one particular day in 2021. So we're modeling quite a bit of fine structure. Some of that is being driven by features of the landscape, both topoclimatic features, but also things like where the major roadways are falling. And then here is a reconstruction of mean temperature on a very hot day in 2021. And then this is zooming in on what the New York City region looks like, and you can actually kind of make out Central Park kind of in the middle of the island of Manhattan there. And so I'll show you some contrasting maps with some other models. So the strength of this pipeline is that it's very highly performant. I'll show you some of our benchmarks. We're able to update it, so we're going to be able to keep up with new developments. People are very interested in, for example, the wildfire events that we had last summer. So we're working now to incorporate data from 2023, and then we're able to make improvements, refine some of this, and then see how that relates to how we quantify health impacts. So I'll show you how this compares with a couple other models. One of the models that we compare with is EPA, the Environmental Protection Agency, produces a daily tract level fine particulate matter estimate, which they call the fused air quality surfaces with downscaling. So they're using a 12-kilometer gridded model called CMAQ, Community Multi-Scale Air Quality Model. And then they're fusing that with the air quality system, the state and locally run monitors across the United States that measure air pollution concentrations using regulatory grade, very high quality instruments. So we were able to sort of benchmark our model against these products that they put out. One of the limitations of their product is that they rely on the National Emissions Inventory, which requires getting information from large source emitters. The EPA sort of brings those data together, and so they're always a couple years behind. So the EPA isn't going to put out the fused air quality surfaces with downscaling, for this year, probably for another 4 years or so. And so it's very hard to do something about what kinds of exposures people have been experiencing if you don't find out about it for quite some time. So we compared our model with theirs for the years that both were available, and we compared it at a bunch of stations that they aren't using in their model. So we trained our model without using those stations as well, so we could have this kind of comparison. And when we they make predictions to the centroid, the center of every tract in the U.S. When we make predictions to the same tract centroids, then looking in centroids where there are these test monitors that neither one used, we have a 16% lower mean absolute error. But we are able to make predictions to exact locations. So when we make predictions to exactly where the monitors are within those census tracts, then we have 22% lower mean absolute error. So we're able to get at some component of local variation even within the tract, right? Whereas one of the assumptions of the EPA kind of putting out one value for every tract is this, they're kind of saying everyone in the tract their exposure can be estimated with this one value in the middle. Sometimes you have to pick something, some sort of central tendency, but this is trying to understand sort of what is the local versus slightly more, let's say, neighborhood level variation. Our temperature, we've compared our temperature to a couple of other gridded temperature products that people have, and so we have much lower prediction error. And one of the ways it's hard to evaluate your model against someone else's if you don't know what data they've already used. Because if they've used those data in training their model, they should do really well on that because they've already peeked at the answers. So to evaluate our temperature model, we actually downloaded data from people's private weather stations. So these are probably nerdy people that have weather stations in their backyards. We picked 10,000 of them across the country, and that's how we do our comparison. And then, so here's a figure on the left is the Oak Ridge National Labs DayMet, which is a 1-kilometer gridded model over the New York City region. And then on the right is our representation of the heat on that same day. And I think this is, it's a daily minimum temperature. So minimum temperatures are happening in the sort of very early morning hours. But minimum temperature has a lot of implications for human health because, if you don't get a chance to cool down at night, if you don't get that physiologic respite, then that's when heat really starts to take some of its toll. So what are the implications of having better models? Why do we go to all this trouble? I already mentioned there's lots of other products out there. The EPA is distributing something. Why restart this whole thing? So I'll show you some comparisons of what we see. The CDC, some of their metrics on heat and health rely on the North American Land Data Assimilation Systems. That's this larger grid. So you see these big chunkier gray box. And then down below that is a 1 kilometer, we built an hourly model. So we're able to sort of compare, what are the implications of assigning everyone in that bigger grid the same value versus having this finer resolution instead of 11 by 13 kilometer, this 1 by 1 kilometer. So we have lower mean squared error. We have about a third of the mean squared error versus this NASA product that the CDC is using. And so then we looked during a heat wave, what are people being exposed to in terms of temperature, and how does that relate to their metrics of social vulnerability, which is put out by the census, uses data from the census put out by the CDC at the tract level. So we fit a model for the variation within each county, so sort of comparing people that are in pretty compact regions. How does temperature vary with social vulnerability? And so what we find is that if you start to use a chunkier, blockier kind of exposure model, you're lumping people together and you're going to underestimate disparities. So think about 11 by 13 kilometers in Providence, right? Would really be saying everyone's falling in the same pixel, everyone's really experiencing the same thing, and we know that that's not true. So here's some examples in New York State, looking at a few different counties. So this is showing 4 different counties, 2 picked from New York City and 2 picked from upstate. And so what we see on the right is that our model shows this, very different slopes in the relationship between social vulnerability and temperature. And on the left, everyone's kind of getting lumped into one of just a few pixels, these really coarse assignments. And so you would underestimate the differences in social vulnerability if you lump people together. Because of residential segregation and structural racism, we know that there are quite substantial disparities in where people are, and therefore it's really important to understand that there's disparities in what people are exposed to. So we find that we're comparing the sort of most vulnerable to the least vulnerable tracts. We see a 0.7 degrees Celsius difference in a heat wave, right? But if you had used this NASA product, you would have set up, 0.2 degree difference there. So that's the result of a analysis using every tract in every county in 13 Northeast states from Maine to Virginia. So the graphic is just 4 counties, but the effect estimates are from a multi-level model for the Northeast. We have a new preprint that's under review now where we're quantifying residential segregation and summertime air temperature, sort of cumulative metrics related to the cooling energy needs that you would have looking at racial and ethnic disparities across those Northeast states. And the confidence intervals are wider because Rhode Island is a smaller population, but given its density and extreme residential segregation, we do find that Rhode Island has the largest disparities in air temperature, in summertime air temperature of any of these states that we looked at in the Northeast. And that's really seen, Rhode Island stands out in several ways. So we did this analysis as well with PM 2.5 air pollution. We did that same kind of modeling nationally, so we used every tract in the 48 states, and we do that kind of analysis comparing how we look at social vulnerability and air pollution with our model versus with, versus if you were to use the EPA's estimates. So we find differences, across the full scale of social vulnerability on the range of 0.7 micrograms per cubic meter, which is, roughly how much average air pollution improves every 3 years in the last 20 years, given the Clean Air Act is quite effective, but not for everyone. And, the EPA, their model, which we show has much lower accuracy, they're also, estimating much lower disparities in air pollution in relation to social vulnerability. So the theme of this work is that better exposure models are revealing sort of previously underestimated disparities, and then we're looking at these health effects. So I was going to mention a couple of our epidemiologic studies and then wrap up. So we're linking to New York State hospitalization records. So I was able to get a hold of the residential address for all hospital admission records in New York State. So I'm working within that very large database, looking at a subset of births that we think might be spontaneous births. And so we're asking the question, why today? What is the contribution of environmental exposures to why someone would deliver early? And we're also generating estimates for the NIH's environmental influences on child health outcomes, so linking to existing children's cohorts, looking at a range of different health outcomes in children. So thinking about early life exposure, including prenatal exposures, the ability to go back in time with satellite data that was collected contemporaneously, but once you have a record of people's residential addresses, you're able to say, okay, what were the ambient concentrations where you lived when, during a particular window of susceptibility. We did some work in New York City, gene-environment interaction, so seeing that the association of air pollution with kidney disease was worse. This is a double hit, that higher air pollution increases your risk for kidney disease, that there's a risk allele in ApoL1 that increases your risk for kidney disease, but higher air pollution and ApoL1 risk allele is even worse, right? This kind of synergy of gene-environment interaction. Recently, I've been doing a lot of work in Mexico using mortality records in particular in Mexico. So we published a case crossover looking at short-term fluctuations, day-by-day variation in air pollution concentration, and how that relates to mortality risks. The air pollution concentrations in Mexico City, they're higher than what we experience in much of the US, but they're sort of more consistent with what's globally representative, and they're not as high as they were in the 90s, which is good. So we have this large analysis, and so we're able to see these associations, per 10 micrograms per cubic meter in PM 2.5. When you look at the cumulative deaths over a 1-week lagged period, we see these differences in cause-specific mortality for causes that lots of people have recorded are associated with higher air pollution, but also we're able to look, because we did it for every death certificate among adults, at these other sorts of outcomes. So we see that higher air pollution is also associated with cause-specific mortality for deaths that are being labeled as being related to influenza or pneumonia, renal failure, diseases of the liver, and some of those associations are quite strong and striking. So we have some work that we've been working on to try to identify susceptible subpopulations, because that can be used to target future public health efforts. So this is sort of the overall association with air pollution and mortality in Mexico City, but then we also broke it down into many different group-specific categories. And so, for example, we see among females, respiratory mortality, circulatory mortalities have some of the strongest associations, and then in males, respiratory mortality, different demographic subgroups. So we are combining epidemiologic models. You can bring in climate projections. So if you see, associations with a given kind of exposure at this level, then one of the things that people do with this is called health impact analysis. And so you can compare different policy scenarios, and that can help with quantifying some of the burdens or benefits of taking particular pathways or considering particular interventions. And a place in Mexico where we're trying to be influential is trying to help the PROARE, which is the sort of air quality planning for central Mexico. They're trying to decide what steps they should be taking to curtail emissions, and thinking about the health benefits that could afford. Future directions, there's just like a wave of exciting new satellites coming. or that have gone up in the last few years, and that unlocks new kinds of information to quantify exposures. So this is the kinds of information that you get for the hemisphere from a satellite called GOES-16. So GOES-16 is pretty interesting because it's geostationary, which means it's always overhead. And so GOES-16 is actually getting these estimates on a 10-minute frequency during the daytime. So just that's part of the staggering volume of data. But it's primarily a meteorologic instrument. It's how we get incredible videos when hurricanes are forming, particularly. But there are many applications of the data that come in, and I'm hopeful that this is going to become an emergent tool in monitoring rapidly changing conditions so that we can start to give people near-term forecasts and make decisions. Should we be canceling the soccer game? Should we be telling people to stay indoors? Those kinds of decisions about episodic exposures where we can help maybe shave the peaks of people's exposure. And these peaks, I think, are particularly important because no one breathes 24-hour averaged air. Many of our national ambient air quality standards have to do with 24-hour average air. Some of that is a legacy of how we measured fine particulate matter. We used what's called gravimetric measurements, where you pre- and post-weigh a filter that you draw a certain known volume of air through. And it's sort of easier to send someone back to get that filter if they go at the same time of day. You need to draw enough air through it that you'll be able to measure a difference in the mass on that filter. But in fact, there's really very little epidemiologic evidence about whether peak exposures that are sub-daily they may also be important. And so we have this kind of legislative standard. The Clean Air Act is all based on these 24-hour averages, but people are breathing and experiencing events on a shorter frequency, so it's worth some studying. There's a new instrument that just went up last spring, and they're going to be releasing their data in the next few weeks. They're going to start releasing their products called TEMPO, Tropospheric Emissions Monitoring Pollution. It's a NASA instrument. It's going to give us hourly estimates of several air pollutants with a focus on trace gases over most of North America, including the contiguous United States, but from Puerto Rico through to the Canadian tar sands. And there's a little, let's see if we can get this. Let's see, yeah. So during the daylight hours, it's going to be sweeping. It's also geostationary, so it's fixed in position, but the instrument is going to sort of peak down and point at different parts of North America. And so this is going to help us to, again, look at rapidly changing conditions, whether that's wildfires or industrial accidents. I'm very interested in, power plant emissions. I think that's pretty interesting to see what people are putting up their smokestacks. And of course, Rhode Island is very impacted by the transportation sector. We have a pretty big interstate that runs through. So let's see if I can go back to this. Okay, so satellites are a key tool for monitoring the consequences of climate change. I mentioned PM 2.5, temperature, humidity. They're also useful at measuring trace gases like ozone, nitrogen dioxide, sulfur dioxide. They can be useful in quantifying vegetation and greenness, things like tree canopy height. These play important roles in cooling our neighborhoods, right? So it can be hard to put in big trees, but if you don't start, you won't have them later. And also quantifying wildfires and flaring as examples of particular activities that will, you can see their thermal signature, and so that's one of the ways in which you can kind of think of the concept of sky truthing, keeping track of what people are doing from space, not necessarily being so reliant on things like voluntary emissions reporting. So with that, thank some members of my lab, acknowledge some funding, and happy to take a moment of questions.
So I've heard, or I understand that we get a cloud from New York late afternoon in Rhode Island on a regular basis, so that hourly sensing would be interesting. Has anybody looked at that aspect of things, we get the pollution from the Bronx every afternoon, so.
Yeah, absolutely. So right. So, Michael Geigert's the sort of air quality person for Connecticut and often talks about how, Connecticut is just sort of downwind of New York City, and so it has all these ozone exceedances, has to explain, but you can really see this drift. And so I think understanding where our air pollution comes from can help in targeting and thinking about, how do we create changes that impact, who is downwind. So absolutely, Rhode Island and the Long Island Sound are impacted by, particularly for nitrogen dioxide, and ozone. That's a big player. Also, Corey Ziegler is a biostatistician who's coming to Brown this summer, and he does this work on modeling emissions from each power plant in the country and sort of looking at where the packets of air that came from that power plant end up and how those relate to health outcomes. And so, we're getting some emissions from the Midwest. We're getting some emissions from, quite far away. We certainly saw last summer this story of wildfires that were, in eastern Canadian provinces coming down. And so not everything's in our immediate control, but I think satellites can be a really helpful tool in bringing attention to those problems and saying, here's where we see this is coming from and here's what we need to do for those things that we can change. For those things that we can't change, maybe they can be helpful in giving people the heads up and thinking about what sort of interventions can we have now to decrease the harms as episodic air pollution is coming through. But you're right, not everything is coming out of our own backyard tailpipes. Backyard tailpipes are added on top of it, though, and so part of the inequity in exposure, right, is that there are communities that have all that stuff coming from the greater New York City metro area, plus they've got our own highways running through. So it's an and, it's regional and local. And our models do, because we're able, with the air pollution, we're modeling specific points in space, we're able to pick up, the machine learning has learned, even though it's not a dispersion model, that there are higher exposures associated with being closer to roadways. So, it sort of dissipates after a few hundred meters, but who ends up in that, that first house after the highway is not random, right? It's reflected in real estate prices, and then it's reflected in, zoning, and it's reflected, right? And, where towns and cities end up siting schools, right? It quite often is close to highways because that land ended up being less expensive when it was time, or someone, turned it over to the town or whatever for $1. So we do see lots of local effects that are, I think, really relevant, and they're really missed when you start to just say, oh, everyone in this county or everyone in this neighborhood will be assigned this one number. Yeah, Sharon.
It'll be really interesting to see how Bridgegate affects, let's say, asthma rates in the city of Providence. Presumably there's less traffic, or maybe there's more traffic.
Yeah, so I got asked about that question quite a bit right after it happened, and there's a paucity of information, and our ability to reconstruct what happened is also limited by the the ground monitoring networks that we do have. There are folks at Brown who have set up local monitors, but they weren't perhaps ideally located for monitoring that kind of a situation. It's an interesting one. Providence has very high, asthma rates. Providence has, so there are reasons already to be concerned. And for sure, it's changed traffic patterns substantially. You also saw that people who could stay home were staying home, and so the effects were quite a bit worse on like Tuesday to Thursday, and on Friday it's really not that bad because so it's quite dynamic and interesting. Thank you.